So the average only deals with a period of time, and if we want to ask for the speed or velocity at a particular moment or a particular location, then we have to deal with a new concept. It's called instantaneous velocity and speed. This is a coordinate of t, and this y direction is x, so we call x versus t. So this x is position, this is x versus t graph, position versus time. Now if I give a curve like that, what does that mean? Well, let's take a look at what does that mean. This actually gives us a relationship of, if you choose one point, that we can go ahead and find what is the position on the t. I should say, what is the time moment? So that's called t1. And what's the position? That is called x1. And the next one, I choose the peak, for example. Then we can find what is that at t2. And then what is this? We call x2. So anything on the curve, we can exactly, according to the scale of t and x, we can tell position versus time. If we ask for average velocity, we just learned. Velocity, that's v with arrow. Average is a bar. That is change of position over time. Since this is a position versus time curve, so we can find that x2 minus x1, that's change of position from 1 to 2. And time moment is t2 minus t1. So that gives us average velocity between, if we name this point as point A, next one is point B. However, if we don't like that, we say, well, what is the instantaneous velocity at A? Or what is the instantaneous velocity at B, if we want exactly at that moment t1 or t2, or we say exactly at the position x1, x2, what is the velocity or speed? Then we have to use a very tricky technique. Well, take a look at this. Can we imagine that if B get very close to A, then the average velocity of AB, then it will be very close to the instantaneous velocity of A, because AB are very close to each other. So let's take a look at, right now, if we calculate the average velocity between A and B, according to the delta x over delta t, delta x actually is this much. This is delta x. Delta t is that much. So if I amplify, this is delta x and that is delta t. This is point A and that is point B. So as a matter of fact, if you connect AB, delta x over delta t is the slope of the line which connect AB. So imagine, well, in this case, actually we have a curve, A to B. If B get closer, let's call B of prime, then if you connect A and B, that will be that straight line. Can we imagine B even get closer? Let's call B prime prime. Then it looks like if you connect A and B prime prime, it looks like it becomes tangential to the curve and passing point A. So when we have B prime prime infinitely close to point A, then the average velocity between A and B prime prime becomes the instantaneous velocity of A. So how do we mathematically describe that? We say this. V, that's velocity. At point A, how do we get that? That is delta x over delta t. Either we say when delta t is approach almost 0, because if starting from A goes to P, you allow time change only to be very close to 0. Then that means B point, which is B prime or B prime prime, are very, very close to A. So this is the definition of instantaneous velocity at point A. Well, mathematically, this actually means dx dt, because your delta t is so small, it's close to 0. That is the concept of dt. So instantaneous velocity is simply, mathematically, is dx over dt. Graphically, what is it? That is the slope of that tangential line. The line is tangential to the curve and passing point A. So that is a very interesting result. And obviously, if we talk about instantaneous velocity, then we still have to talk about direction. Right now, from A to B, we move towards positive x direction. So your velocity instantaneous at A is positive. Let's look at this graph. This is the one that position versus time. And we have those nice scale, 0 to 10. So equally marked at 10 to 20, and so on and so forth. And then this, actually we marked origin right here, so you can either move towards positive x direction or you can move towards negative x direction. And this A is obviously at t equal to 0, position looks like 30 of meter. And the B, it looks like position is 50 meter and time moment is 10 seconds. And so we can actually find out the position for C and the time for C, and also for D, E, and F. Now, if I want to ask what is the instantaneous velocity at point A, we just learned that graphically we need to draw a tangential line past point A like that. So the slope of that line will be the instantaneous velocity at point A. So how do we get slope? Well, one point is A, the other point we can choose here. This one, the position obviously is 60. And the time we have to estimate. Say if we think that this is 60% of 0 to 10 seconds, that is in 6 seconds. So what we do is we say VA equals to, well, slope of that tangential line. So that is change of y. So the final point is at 60 meters. At point A, this is around 30 meters. So that is 60 meters minus 30 meters. And the time actually is 6 seconds minus 0. And that is how we get the instantaneous velocity at point A. Very interesting. If we want to apply this concept to get instantaneous velocity at point B, we draw a tangential line past B. The slope of this tangential line is 0 because this line is parallel to the t-axis. Slope is 0. What does that mean? That means VB equals instantaneous velocity at B is 0, which means at this moment the object has no velocity. Why is that? Because look, from A to B, the object moves towards positive x direction. But once after B, it goes down to C, which is going to the other direction, which is the negative direction of x-axis. Anything you want to change direction has to stop first and then turn around. So this is what happened. At point B, the instantaneous velocity, which means at that moment, velocity is 0. Then the object turn around and start to move towards negative direction of x-axis. And then the instantaneous of velocity at B, at the C, the slope is negative. That's fine because negative only means direction of the velocity is towards the negative x-axis. So VC instantaneous, what do? We still do the same thing. So one point is a C, another point we can actually extend. We extend this line, we find it a point right here, So we can find the slope. Again, the final position, let's say it's 20 meters. So it's 20 meters. Initial position is at C. Let's say that's 40. So from 40 meters goes to 20 meters. So we are moving towards the negative direction of x-axis because numbers start to decrease. And the final time moment, let's assume that's 26 seconds. And C is at 20 seconds. So that is how we get, well, still we get the same, it's meter per second as the unit. So that is the instantaneous velocity at C. And that will give us a negative. So we can do the same thing for D, tangential. Then we can do for E. Then we do for F. Now, if we look at them, the slope, it looks like at A has the highest slope because it's steep, and B 0. C is relatively, and the slope is gentle, and D pick up. E also pretty same as D. What does that mean? If we talk about magnitude, the highest speed is at A. Next is C. I should say next is D, because it's kind of steep too. And then C and E are quite same. At F and B, the speed is 0. Now the slope of A is positive, which means the velocity is moving towards positive x-axis. And the slope at C, D, E are negative, which means at point C, D, E, the object moves at a negative direction of the x-axis. So this is a very interesting graph. Next, let's look at this one. This is a graph of x versus t. Probably was, wait a minute, didn't we see that one before? Yes, we saw that one a few minutes ago. This is a amplified regional graph around point A, which means if we want to get instantaneous velocity at A, and initially you can have a point B and you get average velocity between A and B, but when B get closer, see, did you see eventually when B gets so close, A and B are the same point, then the slope of the straight line become the slope of that tangential line. So this is an amplified graph. Now what I try to show you actually is this new graph right here. This is velocity versus time. It's different. This is position versus time. So velocity versus time is more direct because it's simply, say at point A, I can tell what is the V, which is positive, and also if we have scale, we can read the magnitude and that time moment. And then B, I can also find out. So V versus T give you instantaneous velocity right away. However, did you see there's a symbol of A? This is acceleration. What does that mean? Look at point A. At point A, V is Vx of initial. At point B, the V is called Vx final. So point A is the initial point A is final point. Look at this car. This car starts from A and goes to B. It tells us instantaneous velocity at A is positive, it's this value. At B is still positive, but at higher value. This means the car's speed changes. Well, when speed changes, we say there is an acceleration. More specifically, we should say when velocity changes, there's acceleration. Because later, we will realize, even first, if we travel towards east at 5.0 meters per second, and later we travel the same 5.0, but we travel towards west, we say there must be an acceleration. Why? Because initially if we travel towards the east, then we later travel towards the west. How did we do that? If it's along the one-dimensional x-axis, we have to stop first, then we turn around. When we start from 5 meters per second east, then we need to stop. That is a deceleration. Then we turn around, we travel towards west, we have to pick up speed because we just stopped. Finally, we reach 5.0 meters per second. It traveled towards west, and we need to experience acceleration. So therefore, more specifically, the definition of acceleration is, well, we start from average. The acceleration is a vector. Average is change of velocity over change of the time. Okay, let's explore this concept of acceleration. Acceleration, and right now I mark x, which means one-dimensional if we just use x-axis. A bar means average. Well, at this moment, because our delta v is change of velocity, if change of velocity is vector, and then change of acceleration is also a vector. So, well, more precisely, we should say acceleration has an arrow, it's a vector, then we put a bar, and then we say average. Okay. So that is final velocity minus initial velocity, and final time minus initial time. I just explained there's a case, very interesting case. For example, say at t, this is v versus t graph, at t equals to 2.0 second. Our v is 10 meters per second. It's positive. Okay. If I extend my v, this is the v axis, say for example. Now, this is my first point. Let's call initial, right? If next point, let's mark here. That's my final. The final has a value of negative 10 meters per second. And then let's say this is at the time moment of 5.0 of a second. Now, if we want to ask for what is the average acceleration, if you only look for the number of final, this initial velocity, the magnitude, and the final velocity, the magnitude, this is 10 meters per second, this is 10 meters per second. However, this is positive 10, this is negative 10. If we strictly follow the definition, then did you see final initial has an arrow, which means it's a vector? Vector, we have to consider direction. Considering direction means you have to get negative, positive involved because that actually means direction. So, final, we have to plug in negative 10 meters per second. Subtract initial, it's positive 10 meters per second. And the time moment, final is 5.0, initial is 2.0. So take a look. Then we will have a numerator of negative 20, and we have a denominator of 3.0. Now let's look at the units. Since that change of velocity, it's meter per second. Time, change of time is second. So the ratio of meter per second over second give us meter per second square. So the acceleration right here should have meter per second square. So whenever we see meter per second square, that is the units for acceleration. And it's negative means actually the acceleration is this way. What does that mean? Very interesting. Take a look. If we are initially here, and later we're here, how could we do that? Initially we're moving at positive 10 meters per second. Later we move at negative 10 meters per second. So we must slow down. Slow down means we have an acceleration opposite direction of our initial velocity, which we call deceleration. And then we stop. And then we move towards the negative direction of v. So our acceleration is always opposite direction of initial velocity direction. That's why it comes negative. Again, we encounter average and instantaneous. That's two different concepts. Instantaneous gives us the acceleration exactly at that time moment. So again, we say instantaneous is the limit when delta t approaches 0 of delta vx over delta t. So if we use calculus, that will be the instantaneous acceleration defined as dv over dt. That is the mathematical definition. However, if we want to look at a graphic, then it is very interesting. And